Picture this: a cosmic object lurking in the darkness of space, so magnetically powerful it could strip the data from every credit card on Earth in an instant, even from thousands of miles away. Sounds like something straight out of science fiction, right? But here's the terrifying truth. This isn't a fantasy. It's real. Meet the Magnetar, the universe's ultimate magnetic monster. These bizarre, ultra-dense stellar corpses wield magnetic fields trillions of times stronger than anything we've ever created on Earth. Just one of them could warp the very fabric of space around it, twist atoms into spaghetti, and unleash bursts of energy so intense they've been detected clear across the galaxy. What makes these cosmic anomalies even more mind-blowing is how they're born. Imagine a star so massive that when it dies, it doesn't just fade away, it collapses in on itself with such violent force that it leaves behind a core more dense than an atomic nucleus. That's a magnetar. A single teaspoon of its material would weigh billions of tons, and yet, despite their unimaginable density, it's their magnetism that truly defies belief. These celestial powerhouses generate fields so strong they could rip apart molecules from hundreds of thousands of miles away, turning the space around them into a nightmare zone where even the laws of physics start to bend. But here's the real kicker: we've only scratched the surface of understanding these cosmic enigmas. Every time scientists observe one, they uncover something new that challenges everything we thought we knew about magnetism, gravity, and the very limits of matter. What if magnetars hold the key to some of the universe's greatest mysteries, like the origins of fast radio bursts or the strange behavior of space-time itself? Strap in, because today we're diving deep into the heart of these magnetic titans, uncovering their secrets and exploring why they're some of the most fascinating and frightening objects in the cosmos. To truly grasp the insane power of a magnetar, let's put its magnetic field into perspective. Think about the little magnet on your fridge, strong enough to hold up a grocery list but weak enough that you can pull it off effortlessly. Now, imagine a magnetic field so intense it could yank the iron from your blood across a distance equal to halfway to the moon. That's the terrifying reality of a magnetar. While Earth's magnetic field is strong enough to guide compass needles, a magnetar's field is roughly 1 trillion times more powerful. To put it another way, if you could somehow bring a magnetar even 1,000 miles close to Earth, its magnetic grip would erase every hard drive, scramble every electronic device, and turn all our tech into useless junk in an instant. These cosmic monsters aren't just neutron stars, they're neutron stars cranked up to 11. When a massive star, many times heavier than our Sun, exhausts its fuel and explodes in a supernova, its core doesn't just collapse into a typical neutron star. Instead, under extreme conditions like a swirling dynamo of superheated plasma and rapid spin, the newborn star's magnetic field gets amplified to unimaginable levels. The result, a magnetar where the very fabric of reality starts to buckle under its influence. Atoms stretch into thin, noodle-like shapes. Light itself gets twisted as it passes through the warped space around it. And the energy stored in its magnetic field, enough to power our entire civilization for billions of years, if we could somehow tap into it. But the real shocker: magnetars are volatile. Unlike the steady hum of a pulsar, another type of neutron star, magnetars are prone to violent outbursts called starquakes, when their crust, made of ultra-dense neutron star material, cracks under the strain of those insane magnetic forces. They release bursts of X-rays and gamma rays so bright they outshine entire galaxies for a fraction of a second. Some of the most powerful explosions ever recorded in space, like mysterious giant flares, trace back to these unstable cosmic powerhouses. So why haven't we heard more about them? Because they're rare. For every 1,000 neutron stars, only a handful become magnetars, making them some of the universe's most elusive and destructive objects. Yet, every time we detect one, it forces us to rewrite our understanding of physics. Their existence pushes the boundaries of what we thought was possible in the cosmos, proving that reality can be far stranger and far more terrifying than anything we could dream up. The birth of a magnetar is one of the most violent and spectacular events in the universe, a cosmic catastrophe on a scale we can barely comprehend. It all begins with a massive star, at least 8 to 10 times heavier than our Sun, burning through its fuel at an extraordinary rate. For millions of years, it shines brightly, fusing lighter elements into heavier ones in its core. But when it finally runs out of fuel, the star's fate is sealed in seconds. The core collapses under its own gravity, triggering a supernova explosion so powerful it can briefly outshine an entire galaxy. In the chaos of that explosion, something extraordinary happens. Most collapsing stars leave behind a neutron star, a city-sized remnant so dense that a sugar cube-sized chunk would weigh as much as Mount Everest. But under rare conditions, the newborn neutron star doesn't just stop there. If it's spinning fast enough, revolving hundreds of times per second, and has a swirling ocean of superheated plasma trapped in its core, something wild occurs. That rapid rotation, combined with the churning plasma, acts like a cosmic dynamo, amplifying the star's magnetic field to unimaginable levels. The result: a magnetar, a neutron star turned up to an entirely new level of extreme. What's fascinating is that not all neutron stars become magnetars. Most settle into a more stable existence as pulsars, those steady cosmic lighthouses beaming radio waves across the galaxy. But a rare few, thanks to the perfect storm of speed, density, and magnetic chaos, evolve into these terrifying magnetic monsters. Scientists estimate that for every 10 neutron stars, only 1 or 2 cross the threshold into magnetar territory. And here's the wild part: these newborn magnetars don't stay frenzied forever. Over time, their rapid spin slows down, their magnetic fields gradually weakening. But even in their coma state, they're still orders of magnitude more powerful than anything we've ever encountered. Some magnetars may even go through periods of violent reawakening, cracking under magnetic stress and unleashing bursts of energy that remind us just how unpredictable and utterly fascinating these cosmic powerhouses truly are. So how does a magnetar end up with a magnetic field strong enough to warp reality itself? The answer lies in one of the most chaotic environments in the universe, the swirling, superheated chaos of a dying star's final moments. Scientists call it the dynamo theory, and it's the best explanation we have for why these cosmic monsters become so magnetically charged. Picture a star collapsing in on itself, its core spinning faster and faster like a figure skater pulling in their arms. As it spins, the star's interior becomes a churning ocean of plasma, a seething mass of charged particles trapped in a gravitational vice. This is where the magic, or rather the terrifying physics, happens. Those swirling plasma currents act like a giant cosmic generator. Charged particles moving in turbulent loops create electric currents, and those currents, in turn, generate magnetic fields. Normally, this process would produce something we're familiar with, a stable magnetic field like Earth's or even a pulsar's. But in a magnetar, conditions are anything but normal. The newborn neutron star is spinning hundreds of times per second, its core so dense and hot that the plasma flows become wildly unstable. This amplifies the magnetic field exponentially, pumping it up to strengths that would make a lab magnet look like a child's toy. Think of it like revving an engine past its red line. Most neutron stars stabilize, but magnetars push the system into overdrive. Their magnetic fields grow so strong they actually start feeding back into the star's rotation, twisting space-time around them in ways we're still struggling to understand. Some researchers even speculate that the magnetic forces become so extreme they distort the neutrons themselves, stretching them into bizarre, elongated shapes. It's like taking the familiar rules of magnetism and cranking them up to a level where physics textbooks start sweating. And here's the kicker: we've never seen anything like this on Earth. Our strongest man-made magnets pale in comparison, generating fields millions of times weaker than a magnetar's. Even the Large Hadron Collider, with its superconducting electromagnets, can't come close to replicating these cosmic conditions. That's why every new magnetar discovery sends shockwaves through the astrophysics community. They're natural laboratories for extreme magnetism, forcing us to question whether our current models of physics can even handle their insane energy scales. But the dynamo theory isn't without its mysteries. Why do some neutron stars become magnetars while others don't? Is it the initial spin rate, the exact composition of the collapsing star? Or some hidden factor we haven't even considered yet? Every observation raises new questions, making these cosmic powerhouses one of the most thrilling and humbling frontiers in modern astronomy. At first glance, magnetars and pulsars might seem like cosmic twins, both born from the fiery deaths of massive stars, both packing unimaginable density into a sphere no bigger than a city. But peel back the surface and you'll find two wildly different beasts lurking beneath. The key difference comes down to what powers them. Pulsars are the precision timekeepers of the universe, their steady pulses of radiation fueled by relentless rotation. Imagine a spinning lighthouse beam sweeping across the cosmos with clockwork regularity. That's a pulsar, a neutron star rotating so fast it can complete hundreds of turns every second, beaming energy outward like a cosmic metronome. Their brilliance comes from motion, their rotational energy so immense it generates intense electromagnetic waves detectable across interstellar distances. Magnetars, on the other hand, are the untamed rebels of the neutron star world. While they might spin rapidly at birth, it's not their rotation that defines them, it's their unfathomable magnetic fields. These aren't just stronger versions of pulsar fields, they are in an entirely different league. A typical pulsar's magnetic field might be 100 trillion times stronger than Earth's, but a magnetar's field dwarfs that by another factor of 1,000. That difference isn't just academic, it completely changes how these objects behave. Pulsars emit predictable, rhythmic pulses, while magnetars erupt in violent, unpredictable outbursts, their magnetic energies twisting their very crusts until they snap under the strain. Here's another way to think about it. If a pulsar is like a finely tuned sports car humming along at a consistent speed, a magnetar is a nitro-fueled dragster with its engine perpetually redlined. One thrives on stability, the other is a ticking time bomb of magnetic fury. Even their lifespans diverge dramatically. Pulsars can spin steadily for millions of years, their rotations gradually slowing like a wound-down toy. Magnetars, however, burn bright and fast. Their monstrous magnetic fields act like cosmic brakes, sapping their spin energy so quickly that within 10,000 years they're left as sluggish, magnetized husks. Yet for all their differences, both share one eerie trait. They're among the few objects in the universe where physics as we know it starts to break down. Pulsars challenge our understanding of gravity and nuclear matter, while magnetars push magnetism into realms so extreme they might as well belong to another dimension. And that's what makes them so fascinating, their nature's way of showing us just how far the laws of physics can bend before they snap. Measuring the mind-bending strength of a magnetar's magnetic field requires numbers so large they barely make sense to the human brain. Scientists quantify these fields in units called Gauss or Tesla, terms you might recognize from hospital MRI machines, which use magnetic fields around 1.5 to 3 Tesla to peer inside the human body. That's already thousands of times stronger than Earth's magnetic field, which measures a modest 0.00005 Tesla, but a magnetar. It laughs at such puny numbers. These cosmic monsters clock in at around 10 trillion Tesla or 10 quadrillion Gauss, a number so vast it's like comparing a candle flame to the heart of a supernova. To put that into perspective, imagine the strongest magnet ever built on Earth, say, the ones used in cutting-edge physics labs capable of reaching around 45 Tesla. At that strength, metal objects can violently fly toward the magnet, and electronic devices nearby are instantly fried. Now picture a field 10 trillion times more powerful. A magnetar's grip is so intense that if you could somehow hover a mere 600 miles away, its magnetic force would literally pull electrons right out of your atoms, turning your body into a cloud of ionized particles before you even knew what hit you. What's even wilder is how scientists detect these fields from light years away. Magnetars don't come with cosmic measuring tapes, so researchers rely on their X-ray and gamma-ray emissions. When a magnetar's crust cracks under magnetic stress, the resulting starquake releases radiation so distinctive that its energy signature reveals the field's strength. It's like listening to a guitar string's pitch to estimate how tightly it's tuned. Some magnetars even exhibit a phenomenon called cyclotron lines, tiny dips in their X-ray spectra caused by electrons spiraling around magnetic field lines at nearly the speed of light. By analyzing these lines, astronomers can calculate the field's intensity with astonishing precision. But here's where it gets truly surreal. A magnetar's field isn't just strong, it warps the very rules of quantum physics. In ordinary magnets, electrons align to create a collective field. But in a magnetar, conditions are so extreme that the vacuum of space itself becomes magnetic, a state where even empty space is polarized. This bizarre effect, predicted by quantum electrodynamics, means that light passing near a magnetar doesn't just bend. It splits into two separate beams like headlights hitting a cosmic prism. No earthly lab can recreate these conditions, making magnetars one of the universe's ultimate natural experiments. And yet, for all their terrifying power, magnetars are fleeting by cosmic standards. Their monstrous magnetic fields act like brakes, slowing their rotation within tens of thousands of years, a blink of an eye compared to the billion-year lifespans of pulsars. So every time we detect one, we're catching a glimpse of a rare, volatile phase in a neutron star's life, one where the universe flexes its magnetic muscles in ways we're only beginning to comprehend. If you thought earthquakes were terrifying, wait until you hear about their cosmic counterpart starquakes. On a magnetar, these aren't just tremors, they're apocalyptic events where the very crust of the neutron star rips apart under unimaginable magnetic strain. Picture Earth's most violent quakes, then multiply that energy by a billion, and you're still only scratching the surface. When a magnetar's crust, a crystalline lattice of neutron-rich material harder than diamond, finally buckles, it releases more energy in a fraction of a second than our sun emits in an entire year. What triggers these cosmic cataclysms? It all comes down to the magnetar's impossibly twisted magnetic field. Unlike Earth's relatively orderly field lines, a magnetars are tangled like spaghetti in a hurricane, exerting unbearable pressure on the star's surface. Over time, this stress builds until the crust can't take it anymore. The rupture sends shockwaves racing across the star at near light speed, violently shaking its magnetic field like plucking a guitar string made of pure energy. The result, a burst of X-rays and gamma rays so intense it can light up interstellar space like a cosmic flashbulb. The aftermath is even wilder. These starquakes don't just crack the surface, they rearrange the magnetar's entire magnetic architecture. Imagine snapping a rubber band stretched to its limit, but instead of breaking cleanly, it recoils with enough force to rewrite the laws of magnetism around it. Some scientists compare it to a planetary scale version of what happens when tectonic plates suddenly shift, except here, the ground is a super-dense quantum material, and the seismic waves carry enough energy to vaporize entire planets. We've actually detected these eruptions from Earth. In 2004, a magnetar 50,000 light-years away unleashed a starquake so powerful its gamma-ray flash briefly ionized our upper atmosphere, despite being halfway across the galaxy. For a split second, it outshone the full moon in X-rays, a stark reminder that these distant monsters can reach out and touch us across incomprehensible distances. But perhaps the most unsettling part, we still don't fully understand what happens inside a starquake. The crust might shatter like glass, or it could behave more like a superfluid, cracking and reforming in ways that defy earthly physics. One theory suggests the quakes trigger cascading neutron supernova, tiny, localized explosions within the star itself. Every new observation peels back another layer of mystery, proving that when it comes to magnetars, reality is stranger than anything we could invent. Gamma-ray flares from magnetars are among the most violent explosions in the universe, brief, cataclysmic bursts of energy so powerful they can outshine every star in their galaxy combined. These aren't just bright flashes, they're cosmic detonations capable of sterilizing entire solar systems light years away. And in 2004, we got a front-row seat to their terrifying potential when a magnetar named SGR 1860 unleashed a flare so intense it physically affected Earth from 50,000 light-years away. The mechanics behind these flares are as brutal as they are fascinating. Picture a magnetar's crust locked in a perpetual tug of war between gravity's crushing weight and the magnetic field's repulsive force. When the strain becomes too much, the crust fractures like a pane of glass under a sledgehammer. But unlike Earth's earthquakes, where energy dissipates as ground shaking, a magnetar's rupture injects raw magnetic energy into the surrounding space. The star's twisted field lines snap and recoil, accelerating particles to near light speed. The result, a firestorm of gamma rays, the most energetic form of light, that erupts outward in a beam narrower than a laser but more powerful than a supernova. The 2004 event was a wake-up call. At 1944 Universal Time on December 27th, satellites and observatories suddenly detected a pulse of radiation flooding the solar system. In less than 0.2 of a second, SGR 1860's flare released more energy than our Sun emits in 250,000 years. The gamma rays ionized Earth's upper atmosphere, distorting radio signals and temporarily altering the ionosphere's structure, an effect usually caused by solar storms, not something halfway across the Milky Way. If this outburst had occurred within even 10 light-years of Earth, it could have stripped our ozone layer, triggering mass extinctions. What makes these flares even more unsettling is their unpredictability. Unlike supernova, which give astronomers days or weeks of warning as a star destabilizes, magnetar flares strike without preamble. One moment, the star appears quiet. The next, it's vomiting enough radiation to boil oceans off distant planets. Some researchers speculate these bursts might explain mysterious phenomena like fast radio bursts, those enigmatic, milliseconds-long cosmic signals that have puzzled scientists for years. Yet for all their destructive potential, gamma-ray flares also serve as cosmic laboratories. The radiation they emit carries fingerprints of the magnetar's extreme environment, letting scientists probe conditions impossible to replicate on Earth. By studying how these rays interact with interstellar dust and magnetic fields, we're piecing together how matter behaves under the most extreme stresses the universe can muster. Every flare is a reminder magnetars aren't just celestial oddities, they're nature's way of showing us the outer limits of physics itself. Some magnetars have a strange habit of firing off gamma-ray bursts like cosmic machine guns, blasting the universe with repeated eruptions that defy logic. These unruly objects, known as soft gamma repeaters or SGR, behave completely differently from their quieter cousins, and scientists are still piecing together why. While most magnetars unleash occasional starquakes or rare giant flares, SGR seems stuck in a perpetual state of magnetic tantrums, hurling out gamma-ray bursts weeks, months, or even years apart without warning. The key to this puzzle might lie in their twisted magnetic fields. Imagine a rubber band wound tighter and tighter until it starts fraying unpredictably. That's essentially what's happening beneath an SGR's surface. These magnetars likely have fields so knotted and unstable that they're constantly on the verge of snapping. Every time stressed magnetic field lines finally rupture, they release pent-up energy as gamma rays, only for the process to repeat all over again. It's like a cosmic pressure cooker where the lid keeps rattling but never fully blows off. What's even stranger is that not all magnetars evolve into SGRs. Some settle into relative calm after their turbulent births, their magnetic fields stabilizing over thousands of years, but others remain trapped in a cycle of violent outbursts, crackling with energy long after they should have quieted down. One theory suggests SGRs might be younger or more rapidly rotating, their internal dynamos still churning at full throttle, or perhaps their crusts are thinner, making them more prone to fracturing under magnetic stress. The unpredictability of these eruptions makes them both fascinating and frustrating to study. Unlike pulsars, which tick with near-perfect regularity, SGRs refuse to follow any discernible pattern. Some might fire off a dozen bursts in a month, then go silent for years. Others might unleash a single colossal flare before disappearing into obscurity. In 2007, astronomers watched in awe as SGR 0526 erupted over 100 times in a single day, each burst packing more energy than our Sun emits in 3 decades. Yet another magnetar, SGR 1900+14, stayed dormant for decades before suddenly waking up with a flare so bright it blinded space telescopes momentarily. This erratic behavior challenges everything we thought we knew about magnetic fields and neutron star physics. If we could crack the code behind why some magnetars become repeat offenders while others stay quiet, it might reveal deeper truths about how magnetic energy builds, stores, and explosively releases across the cosmos. For now, SGRs remain one of astronomy's most captivating mysteries, cosmic rebels that refuse to play by the rules. The space surrounding a magnetar isn't just empty, it's a warped, seething prison of lethal energy where physics as we know it takes a nightmarish turn. Imagine the star's magnetic field lines not as neat arcs but as chaotic spaghetti strands, twisted and knotted by the magnetar's unimaginable forces. These tangled field lines create a magnetosphere so hostile it makes Jupiter's radiation belts look like a gentle summer breeze. Charged particles, protons and electrons, don't just float here, they're whipped into frenzied spirals, accelerated to near light speed until they scream with radiation. This isn't just theoretical. Picture an electron caught in this cosmic death trap. The moment it enters the magnetosphere, the magnetic field seizes it like an invisible hand, hurling it along those twisted field lines. The particle doesn't travel smoothly, it's jerked and spun violently, a microscopic roller coaster from hell. Each abrupt change in direction makes it emit X-rays and gamma rays, the same way a skidding tire screeches against pavement. Multiply this by trillions of particles, all trapped in this chaotic dance, and you get a magnetosphere that crackles with enough radiation to vaporize any known material in seconds. What's truly bizarre is how space itself behaves here. Normally, empty space is a near-perfect vacuum, but a magnetar's magnetosphere is so thick with trapped particles it acts more like a bizarre, superheated plasma soup. Atoms can't survive intact, they're torn apart instantly, their electrons stripped away and sent spiraling. Even light doesn't escape unscathed. Photons trying to pass through this mess get twisted by a phenomenon called vacuum birefringence, where the magnetosphere acts like a cosmic prism, bending different wavelengths in opposite directions. It's as if the very fabric of reality is being combed through a magnetic filter. And here's where it gets even stranger. The magnetosphere isn't static, it's alive with seismic shifts. When the magnetar's crust cracks in a starquake, the entire magnetic field structure convulses, snapping and rebounding like a gargantuan rubber band. These magnetic quakes send shockwaves through the trapped particles, triggering cascades of new radiation bursts. Scientists believe this is why some magnetars suddenly flare without warning. Their magnetospheres are pressure cookers, and every tiny adjustment can set off a chain reaction of violent particle acceleration. The sheer violence of this environment defies earthly comparison. If you could somehow shield a spacecraft and fly it into a magnetar's magnetosphere, the radiation would not just fry electronics, it would unravel matter at the atomic level. DNA would be shredded instantly, metals would vaporize, even the strongest theoretical materials would dissolve like sugar in boiling water. And yet, paradoxically, these lethal zones are also cosmic gold mines for astrophysicists. By studying how particles behave in such extreme magnetic fields, we're glimpsing physics that no lab could ever recreate, conditions so extreme they might reveal secrets about quantum theory, the birth of the universe, and the fundamental nature of spacetime itself. This is why magnetars aren't just celestial oddities, they're the universe's most unforgiving classrooms. Every flicker of radiation from their magnetospheres carries encoded lessons about how matter and energy interact when pushed beyond any sane limit. And with each new observation, we're forced to rewrite the textbooks, humbled by how much we still don't understand about these magnetic monsters lurking in the dark. While pulsars announce their presence with rhythmic radio pulses, magnetars whisper in a far deadlier language, X-rays. This eerie glow isn't fueled by rotation like their pulsar cousins, but by something far more exotic, the slow, violent decay of their unimaginable magnetic fields. Every second, as those trillion Tesla fields twist and fray, they inject energy directly into the magnetar's superheated crust, turning it into a cosmic X-ray beacon visible across interstellar space. The Chandra X-ray Observatory has been our window into this process, capturing details that would have been science fiction a few decades ago. Take Magnetar 1E2259-586, discovered in 2001. Chandra's images revealed something astonishing, an X-ray halo surrounding the star, not from its surface but from particles trapped in its magnetic grip. As those particles spiral along field lines, they emit X-rays like frenzied fireflies, creating a luminous cage of energy half a light-year wide. This isn't just light, it's a roadmap of the magnetar's decaying magnetic architecture. What makes this glow even more intriguing is how it differs from pulsars. A pulsar's radio waves come from beams shooting from its magnetic poles powered by spin. But a magnetar's X-rays emanate from its entire surface, heated internally by magnetic decay, like comparing a flashlight to a red-hot iron. Some magnetars, like SGR 0501 plus 4516, even pulse in X-rays, but the mechanism is completely different. Instead of a spinning lighthouse effect, their pulses come from crustal hotspots where magnetic energy erupts through cracks, like lava oozing through tectonic plates. Chandra's observations have also uncovered magnetars where the X-ray output fluctuates wildly, sometimes surging 100-fold in hours. These aren't random fluctuations, they're magnetic reconfigurations in action. Imagine a power grid short-circuiting but on a stellar scale. One moment the field lines are stable, the next they snap and reconnect, dumping pent-up energy into the crust. These events, called anti-glitches, actually slow the magnetar's rotation slightly, proving the magnetic field isn't just decaying, it's actively stealing spin energy to fuel its X-ray fury. Perhaps the most revealing discovery came in 2013, when Chandra caught Magnetar SGR 0418 plus 5729 in a quiet state. Its X-ray output dropped to a whisper, allowing astronomers to detect something unprecedented: thermal radiation from the actual surface. This tiny trickle of heat, just a few million degrees, was the smoking gun, proof that magnetars cool from the inside out as their magnetic engines sputter. It's like finding the embers of a dying forge, still glowing faintly beneath layers of cosmic ash. These observations paint a startling picture. A magnetar's X-rays aren't just a byproduct, they're the death throes of its magnetic field, a slow-motion collapse we're privileged to witness. Every photon carries clues about how matter behaves under conditions so extreme they redefine the word extreme. And with each new Chandra revelation, we're decoding the final, violent chapters of these magnetic titans' lives, one X-ray whisper at a time. Normally, when a neutron star spins down, it's a gradual process like a top slowly losing momentum over thousands of years, but magnetars laugh at normal. In rare, jaw-dropping moments, these cosmic rebels do the exact opposite of what astrophysicists expect. They hit the brakes hard, slowing their rotation in abrupt, violent jolts astronomers call anti-glitches. Picture a spinning ice skater suddenly flinging their arms out to stop, except the skater weighs 2 suns and the arms are magnetic fields powerful enough to shred planets. That's the sheer absurdity of an anti-glitch. The first time scientists witnessed one, it upended decades of neutron star theories. In 2012, the Magnetar 1E2259-586, already famous for its X-ray outbursts, dropped a cosmic bombshell. Over just 36 days, its rotation rate plummeted by a staggering 2 millionths of a second per second. That might sound tiny, but for an object spinning once every 7 seconds, it's like slamming the brakes on a freight train moving at light speed. Even stranger, unlike normal glitches when neutron stars suddenly speed up, this event pumped energy out of the star's spin and into its already apocalyptic magnetic field. So how does a magnetar pull off this bizarre trick? The leading theory involves its crust cracking under magnetic stress, but not like a simple earthquake. When the star's interior magnetic field, twisted like a bundle of over-tightened guitar strings, finally snaps, it unleashes a shockwave that literally rearranges the star's outer layers. Some researchers compare it to a frozen lake suddenly fracturing, except here the ice is a crystalline crust harder than diamond, and the cracks release enough energy to briefly rewire the magnetar's entire rotation. What's wild is that anti-glitches might be linked to magnetar's other freakish behaviors. The same twisted magnetic fields that trigger starquakes and gamma-ray flares could also be yanking on the star's superfluid core, a bizarre quantum soup where neutrons flow without friction. If part of this superfluid suddenly gets pinned to the crust by magnetic forces, it could transfer angular momentum in reverse, stealing spin energy instead of adding it. Think of it like a car's transmission slipping into neutral, then abruptly shifting into reverse, except the car is a city-sized quantum object operating under physics we barely understand. Every anti-glitch discovery forces scientists back to the drawing board. In 2020, another Magnetar SGR 1935+2154 pulled the same stunt, slowing down abruptly after years of steady rotation. But this time, telescopes caught something new, a simultaneous X-ray burst that clinched it. Anti-glitches aren't isolated events. They're part of Magnetar's chaotic lifestyle, where magnetic energy and rotational motion are locked in a constant, violent tug of war. Here's the real kicker. We might be seeing only the tip of the iceberg. Some theorists speculate that anti-glitches could be far more dramatic in younger magnetars, possibly even causing magnetic eruptions that fundamentally alter the star's spin. Others wonder if these events leave permanent scars, twisting the star's magnetic axis or creating long-term instability. With each observation, we're glimpsing a side of neutron stars nobody predicted, where the laws of physics don't just bend, they shatter. A magnetar's life is a cosmic drama in 3 acts, each more extreme than the last. Act 1 opens with a bang, the star's birth in a supernova so violent it briefly outshines its entire galaxy. Fresh from this explosive debut, the young magnetar enters its most chaotic phase, spinning hundreds of times per second like a deranged cosmic top. Its magnetic field, freshly amplified by the dynamo effect, is at peak strength, trillions of times more powerful than Earth. This is the era of hyperactive flares, where the star crackles with pent-up energy, launching gamma-ray bursts like cosmic tantrums. The crust, still hot from formation, fractures under magnetic stress every few years, each starquake unleashing enough X-rays to outshine a supernova for milliseconds. It's as if the universe built a cosmic pressure cooker and forgot the relief valve. As millennia pass, the magnetar enters its middle age, still dangerous but settling into a rhythm. Rotation slows as magnetic braking siphons off spin energy, reducing flares from apocalyptic outbursts to mere city-leveling events. The star now shines steadily in X-rays, its surface glowing at millions of degrees from magnetic decay heat. This phase reveals the magnetar's true nature, not a pulsing beacon like its cousin the pulsar, but a smoldering ember of magnetic fury. Chandra X-ray observatory images show some middle-aged magnetars wrapped in glowing halos, traces of particles still spiraling along decaying magnetic field lines. The once unstable crust thickens, making starquakes rarer but no less violent when they occur. The final act is a slow fade into obscurity. After 10,000 to 100,000 years, a blink in cosmic time, the magnetic field weakens below the quadrillion Gauss threshold. X-ray emissions dwindle as the star's internal dynamo sputters out. What remains is essentially a neutron star with an identity crisis, too magnetically weak to qualify as a true magnetar, yet still packing a magnetic punch millions of times stronger than ordinary pulsars. Some theorists speculate these X-magnetars might explain mysterious isolated neutron stars discovered floating between galaxies, silent, cooling relics of forgotten cosmic fury. Yet even in death, magnetars leave fingerprints. Their twisted magnetic fields may persist for eons, warping space around them like invisible scars. A few might get a second act if stellar collisions or accretion revives their dormant dynamos. And occasionally, astronomers catch a glimpse of ancient magnetars flaring weakly like ghosts, reminding us that these magnetic monsters never truly die. They just fade into the dark, taking their secrets with them. Even among magnetars, some stand out not just for their power, but for their unsettling proximity to Earth. Take SGR 1806-20, for example. This cosmic powerhouse sits about 50,000 light-years away in the constellation Sagittarius, nestled within our own Milky Way. While that might sound comfortably distant, consider this. In 2004, its gamma-ray flare, the brightest ever recorded, briefly disturbed Earth's ionosphere from halfway across the galaxy. If a magnetar that far away can affect our planet, imagine the implications of one lurking even closer. Then there's SGR 0501+4516, located roughly 16,000 light-years from Earth in the constellation Monoceros. Discovered in 2008, this magnetar is relatively quiet compared to its explosive siblings, but its X-ray pulsations reveal a magnetic field crackling with pent-up energy. What makes it particularly intriguing is its youth. Astronomers estimate it's only a few thousand years old, meaning we're catching it at the peak of its magnetic fury. But the real eyebrow-raiser is SGR 0526-66, sitting just 1,600 light-years away in the Large Magellanic Cloud. That's practically next door in cosmic terms. In 1979, it unleashed a gamma-ray burst so intense it saturated detectors across the solar system, proving that magnetars don't need to be galactic neighbors to make their presence felt. Proximity matters for two reasons: science and survival. The closer a magnetar is, the clearer its emissions are, allowing telescopes to capture details like crust vibrations, magnetic field shifts, and even surface hotspots. But there's a darker side. A direct gamma-ray flare from a magnetar within 10 light-years could strip Earth's ozone layer, triggering mass extinctions. Thankfully, none that close are known to exist yet. The universe is vast and magnetars are elusive. Every new discovery reminds us we're living in a cosmic shooting gallery, surrounded by magnetic monsters we're only beginning to understand. The Milky Way is littered with cosmic landmines, magnetars we've only begun to uncover, their identities pieced together through fleeting clues rather than direct observation. Take CZU J17-1405.7-381031 lurking near the center of our galaxy. Astronomers didn't spot it through dramatic flares or pulsing X-rays. Instead, they noticed something strange, a cloud of high-energy particles glowing suspiciously bright in gamma rays with no obvious power source, the smoking gun. The cloud's energy signature matched exactly what you'd expect if an invisible, ultramagnetic neutron star was pumping particles into space like a cosmic particle accelerator. This detective work reveals how most magnetar candidates are found through their aftermath, not their outbursts. Some, like Swift J1834.9-0846, betrayed their presence by heating a nearby debris field to millions of degrees long after their visible light faded. Others, like 3XMM-J1-85246+00333205, were caught in the act of slowly vaporizing a companion star, their magnetic fields ripping material away in fiery streamers. Even stranger are the quiet magnetars like SGR-J0418+5729, which emits no detectable radio waves, just a steady, ominous X-ray glow that fluctuates unpredictably, hinting at magnetic turmoil beneath the surface. The challenge with these hidden monsters is their elusiveness. Without periodic flares, they blend into the galactic background until some anomaly, a sudden temperature spike in a gas cloud, or odd distortions in passing radio waves gives them away. Advanced telescopes like NuSTAR and the upcoming Athena mission are changing the game, though, by scanning for hard X-rays, the kind produced when relativistic particles slam into magnetic fields. They're uncovering magnetars masquerading as ordinary neutron stars. One candidate, PSR J1119-6127, was flagged solely because its X-ray emissions flickered in a way no normal pulsar should. Yet for every magnetar we identify, there are likely dozens more hiding in plain sight. Statistical models suggest the Milky Way could harbor 30 or more of these magnetic beasts, many lying dormant between eruptions. Some might even be disguised as mundane gamma-ray sources, their true nature waiting to be unmasked by the next generation of observatories. And that's what makes this hunt so thrilling. Every new candidate forces us to rethink where and how these cosmic monsters can lurk, rewriting the map of our galaxy's most extreme neighborhoods. While most known magnetars lurk within our Milky Way, a few defiant outliers have been caught blazing across the intergalactic void, cosmic exiles, proving these magnetic monsters aren't confined to our galactic neighborhood. Take the magnetar in NGC 253, a spiral galaxy 11 million light-years away, detected in 2008 by NASA's Swift satellite. This celestial fugitive erupted with a gamma-ray burst so luminous it briefly drowned out its entire host galaxy. That's like spotting a single light bulb in Los Angeles from New York, except the bulb is a hypermagnetized stellar corpse screaming across 11 million years of cosmic history. Observing such distant magnetars pushes astronomy to its limits. Unlike Milky Way magnetars, whose X-ray glows and periodic pulses can be tracked for years, extragalactic ones often vanish before follow-up observations begin. The NGC 253 magnetar, for instance, flared for just 3.6 seconds, a blink-and-miss-it event requiring lightning-fast telescope coordination. Even then, the data arrives diluted by unfathomable distances. A magnetar's X-ray signal, already faint by astronomical standards, gets stretched and reddened as it traverses expanding space, like a voice echoing down an ever-lengthening tunnel. By the time these photons reach Earth, they're often mere whispers in detectors, requiring supercomputer processing to tease apart from background noise. Yet these intergalactic interlopers offer priceless insights. Their sheer brightness during outbursts acts as a cosmic yardstick, allowing astronomers to measure intergalactic distances with unprecedented precision. The gamma rays from NGC 253's magnetar, for example, helped calibrate the galaxy's position in the local group, refining our cosmic map. Even more crucially, extragalactic magnetars serve as uniformity checks. By comparing their properties to Milky Way specimens, scientists confirmed these objects obey the same physics whether they're next door or halfway across the observable universe, a testament to nature's consistency. The challenges don't end with detection. Unlike local magnetars where radio telescopes can pinpoint positions down to millisecond arcs, extragalactic ones often appear as Chinese letter smudges in galaxy-wide surveys. Pinpointing their exact birthplace requires catching them mid-eruption, then cross-referencing with optical and infrared maps to identify host star clusters or supernova remnants. This detective work recently paid off with the Magnetar in Messier 82, a starburst galaxy 12 million light-years away. Hubble images later revealed it originated in a densely packed star-forming region, proof that even in foreign galaxies, magnetars prefer the chaotic neighborhoods where massive stars live fast and die violently. The Holy Grail would be spotting a magnetar in the Virgo cluster, 54 million light-years distant. At that range, even their most violent flares would barely register above cosmic background static. Yet upcoming instruments like the Vera Rubin Observatory and the European Space Agency's Athena X-ray telescope could change the game. With sensitivity hundreds of times greater than current scopes, they might catch these intergalactic ghosts in the act, revealing whether magnetars in other galaxies play by different rules or if magnetism's extremes truly are universal. Every flicker from across the void forces us to wonder, are we seeing cosmic outliers or just the first hints of a hidden population lurking in the darkness between galaxies? For decades, fast radio bursts have been one of astronomy's most perplexing mysteries. Brief, intense blasts of radio waves packing more energy than the sun emits in days, yet lasting just milliseconds. These cosmic flashes seem to come from nowhere, vanishing before scientists could pinpoint their origins. Theories ranged from colliding neutron stars to alien civilizations until April 2020, when a magnetar in our own galaxy decided to break the silence. The object in question, SGR 1935 + 2154, had been a known magnetar, quietly spinning in the constellation Vulpecula about 30,000 light-years away. Then, without warning, it unleashed something unprecedented. A millisecond radio burst strikingly similar to those distant FRBs. Telescopes around the world caught the event, and the data was undeniable. For the first time, we had a smoking gun linking these enigmatic signals to magnetars, not in some far-off galaxy, but right in our cosmic backyard. What makes this connection so explosive is the sheer energy match. The Milky Way magnetar's burst, though fainter than extragalactic FRBs, displayed the same telltale fingerprint, a pulse of polarized radio waves sweeping downward in frequency like a celestial slide whistle. This frequency drift, caused by interaction with magnetized plasma, is the hallmark of FRBs. Here was proof that at least some of these cosmic flashes could be produced by magnetars in moments of extreme magnetic violence, likely during starquakes or magnetic reconnection events where field lines snap and realign catastrophically. But the story doesn't end there. The 2020 detection raised more questions than it answered. Why are most FRBs thousands of times more energetic than SGR 1935's burst? Some researchers argue that extragalactic magnetars might operate under even more extreme conditions, perhaps younger, faster spinning, or embedded in denser environments that amplify their radio emissions. Others speculate that repeating FRBs could come from magnetars trapped in binary systems, where interactions with a companion star periodically trigger outbursts. Then there's the puzzle of diversity. Not all FRBs look alike. Some are one-off blips while others repeat unpredictably. Some show complex substructure with multiple peaks in their radio signals. This suggests that while magnetars might explain some FRBs, the full picture likely involves multiple cosmic phenomena. It's possible that what we call FRB is actually a catch-all category for different high-energy events that happen to produce similar radio signatures. The most tantalizing clue from the Milky Way magnetar was its X-ray counterpart. Just before the radio burst, space telescopes detected a simultaneous flare in higher energy wavelengths, something rarely seen with extragalactic FRBs. This raises the possibility that FRBs might sometimes come packaged with X-rays or gamma rays, but those signals are too faint to detect across intergalactic distances. If true, future observatories could hunt for these multi-wavelength counterparts to confirm magnetar origins. Critics point out gaps in the theory. If magnetars are responsible, why don't we see FRBs from the dozens of known magnetars in our galaxy more often? One explanation is that FRB-like bursts require perfect storm conditions, a specific alignment of magnetic field geometry, crustal stress, and particle acceleration. Another possibility is that we've been unlucky with timing. Magnetars might emit FRBs only during rare, ultra-violent episodes separated by years or decades of quiet. The debate is far from settled, but one thing is clear. The 2020 detection cracked open a window into one of the universe's most baffling phenomena. Every new magnetar outburst, whether in the Milky Way or beyond, is now scrutinized for FRB connections. With upgraded radio arrays like the Deep Synoptic Array and the Square Kilometre Array coming online, we're on the verge of solving whether magnetars are the sole culprits, or if the cosmos has even stranger tricks up its sleeve. At the extremes of a magnetar's grip, even the fundamental building blocks of matter start to unravel. Quantum electrodynamics, the branch of physics governing how light and charged particles interact, predicts something startling when magnetic fields reach 1 trillion Tesla or more. Atoms, normally symmetrical spheres, twist into grotesque, cigar-shaped distortions under this unimaginable pressure. Picture a hydrogen atom, its electron orbiting the nucleus in a neat cloud. Now crank up the magnetic field to magnetar levels, and that electron's path contorts into an elongated spiral, squeezed along the field lines like taffy. The atom itself stretches thin, its shape warped beyond recognition by forces stronger than anything in our universe, except perhaps the singularity of a black hole. This isn't just theoretical fancy. The equations of quantum electrodynamics break down under such conditions, revealing behaviors so bizarre they border on science fiction. Take something called the Landau radius, the minimum distance an electron can maintain from its nucleus in a magnetic field. On Earth, this distance is negligible. Near a magnetar, the field compresses it so drastically that electrons are practically glued to their atoms, altering how chemical bonds form. In essence, the very rules of chemistry rewrite themselves. Oxygen might not behave like oxygen. Carbon could lose its ability to form the intricate structures essential for life. It's a realm where matter itself becomes unfamiliar, reshaped by forces that defy earthly logic. The most mind-bending prediction: at sufficiently high magnetic strength levels some magnetars might actually achieve, the vacuum of space itself becomes polarized. Empty space isn't truly empty. It's a seething quantum foam of virtual particles popping in and out of existence. A magnetar's field yanks on these particles, aligning them like iron filings near a lab magnet. This vacuum birefringence bends light in ways Einstein never envisioned, splitting photons into two distinct paths as if space itself has grain like wood. Even light can't escape unscathed from a magnetar's domain. What's wild is that we've glimpsed hints of this in nature. When X-rays from distant magnetars pass through their own magnetospheres, their polarization patterns match quantum electrodynamics predictions, tangible evidence that these theories hold up even in the universe's most punishing environments. It's as if magnetars are cosmic laboratories, conducting experiments no Earth-bound scientist could ever replicate. They force us to confront the limits of our knowledge, revealing where the rulebook of physics needs new pages, or perhaps an entire rewrite. Yet the full picture remains tantalizingly out of reach. Some models suggest that under truly extreme fields, protons and neutrons, the particles inside atomic nuclei might deform as well, stretching into strings or even flattening into pancakes. If true, this would mean magnetars don't just distort atoms, they redefine the nature of matter at its most fundamental level. Every new observation pushes the boundary of what we thought possible, proving that when it comes to magnetars, the universe still holds cards it hasn't shown us. Buried beneath the crushing gravity and swirling magnetic storms of a magnetar lies one of the universe's strangest materials, a bizarre quantum landscape scientists call nuclear pasta. Far from ordinary matter, this crust isn't made of atoms as we know them. Instead, it's a chaotic tangle of protons and neutrons squeezed into shapes so extreme they defy conventional physics. Spaghetti-like strands, flat lasagna sheets, and even hollow bubbles, all frozen in a crystalline lattice denser than any substance ever created on Earth. To understand how this cosmic oddity forms, picture the magnetar's surface, a seething, ultra-dense layer where gravity is 200 billion times stronger than what we experience. Here, the immense pressure crushes atomic nuclei so close together they merge, dissolving into a sea of nuclear matter where individual protons and neutrons jostle like grains in a cosmic sandstorm. But it's the magnetar's monstrous magnetic field, trillions of times stronger than Earth's, that sculpts this chaos into something even wilder. Those unimaginable forces stretch and twist the nuclear material, warping it into shapes straight out of a quantum nightmare. The pasta analogy isn't just poetic, it's shockingly accurate. At the top layers, where pressure is slightly lower, nuclei elongate into long, thin tubes dubbed spaghetti. Deeper down, they flatten into expansive sheets resembling lasagna. And in the deepest regions, the competing forces of gravity and magnetism carve out voids, empty pockets fringed by neutron-rich walls, earning them the name nuclei. These structures aren't static, they're constantly shifting under the star's magnetic turbulence, cracking and reforming like ice sheets on a roiling ocean. What makes nuclear pasta even more alien is its strength. Simulations suggest this material could be 10 billion times stiffer than steel, yet it's not indestructible. When the magnetar's magnetic field twists too sharply, the pasta-like crust snaps, triggering starquakes that release more energy than a billion atomic bombs. These fractures might also explain magnetar's mysterious X-ray flares. As chunks of crust shatter, they expose the star's superfluid interior, unleashing tsunamis of particles accelerated to near light speed by the magnetic field. The real mind-bender: we might never replicate this material on Earth. Laboratories can't generate pressures or magnetic fields intense enough to forge nuclear pasta, which means magnetars are our only window into this exotic state of matter. Every flicker of X-rays or gamma rays from their surfaces carries clues about how matter behaves when pushed beyond the limits of known physics. And that's what makes these cosmic kitchens so invaluable. They're cooking up recipes for matter that don't exist anywhere else in the universe. Near a magnetar's surface, time itself begins to falter, not metaphorically, but in ways that would make Einstein's head spin. Thanks to the star's colossal gravity, the fabric of spacetime warps so drastically that clocks here would tick agonizingly slow compared to those on Earth. This isn't science fiction, it's general relativity in its most extreme form. Picture an astronaut hovering just above the magnetar's crust, ignoring for a moment that they'd be vaporized instantly. For every second passing on their crippled wristwatch, years could whip by for distant observers. The star's gravitational grip stretches time like taffy, bending it to the point where causality itself starts to stutter. The numbers are staggering. A magnetar's surface gravity is typically 20 trillion times stronger than Earth's, enough to squash spacetime into a profound well. If you could somehow survive near one, time dilation would be so severe that just 5 minutes of your experience might equate to a decade back home. This isn't just a tweak, it's a fundamental rewiring of reality. Even light struggling to escape the magnetar's pull pays a toll, its wavelength stretched and reddened as if exhausted by the climb. What makes this even wilder is how magnetism complicates the effect. While gravity warps time, the magnetar's ludicrously strong magnetic field also influences spacetime in ways Einstein never anticipated. Recent theories suggest that at field strength above 10 billion Tesla commonplace for magnetars, the vacuum of space becomes polarized, altering how time flows in ways not fully understood. It's as if the star's magnetism and gravity are locked in a tug of war over the very meaning of now. And here's the real kicker, we've actually measured this. In 2012, astronomers studying the Magnetar SGR 0418+5729 detected X-ray pulses slowed by time dilation. The star's rotation, mapped over years, revealed tiny discrepancies matching relativistic predictions, proof that even magnetars can't cheat Einstein's rules. These observations aren't just academic, they're stress-testing general relativity in environments no lab could ever replicate, probing whether the laws of physics hold under such inhuman strains. Yet mysteries remain. Some magnetars exhibit time dilation effects slightly stronger or weaker than models predict, hinting that our understanding of spacetime might still be incomplete. Could their magnetic fields be warping time independently of gravity? Or is there some exotic quantum effect at play in their cores? Every flicker of distorted light from these cosmic time benders forces us to reconsider what we thought we knew about the universe's most fundamental structure. Approaching a magnetar would be the most spectacularly bad idea in the history of space exploration, a suicide mission where physics itself turns against you in increasingly creative ways. Long before your ship crossed the magnetar's event horizon, its magnetic field would begin rewriting the rules of your existence. At a distance of 100,000 miles, roughly halfway to the moon, the field strength would already surpass 1 billion Tesla. Your ship's metal hull would instantly become a death trap, warping under forces strong enough to rip electrons from atoms. Every circuit would fry as magnetic induction turned wiring into makeshift particle accelerators, blasting your electronics with rogue currents. Even non-metallic materials wouldn't be safe. Organic molecules like those in your body contain charged particles that would align violently along the field lines, distorting cell membranes and unraveling DNA like zippers caught in a hurricane. As you crept closer, the real nightmare would begin. Around 60,000 miles out, the magnetar's field would start pulling iron directly from your bloodstream. Hemoglobin molecules, normally harmless oxygen carriers, would transform into microscopic grappling hooks, wrenching themselves toward the star with enough force to tear through blood vessels. Your nervous system would short-circuit as ion channels, the delicate electrical wiring of your brain snapped under magnetic stress. Consciousness would flicker out long before your body succumbed to the rising heat, cooked by eddy currents induced in your tissues. Survival wouldn't just be improbable, it would be geometrically impossible. At 30,000 miles, the tidal forces would come into play. A magnetar's gravity is strong enough to stretch and compress objects simultaneously, creating stresses no material could withstand. Your ship and your body would undergo spaghettification, elongating into a thin stream of plasma as differential gravity pulled harder on your near side than your far side. The process would be mercifully quick. At these distances, the magnetar's X-ray flux would deliver a radiation dose millions of times lethal levels, sterilizing your remains before they could even finish disintegrating. But the true horror lies in the quantum absurdity awaiting any object that somehow survived to touch the surface. The magnetic field would be so intense that atoms themselves would distort into pencil-thin shapes, their electron orbitals stretched beyond recognition. Chemical bonds, the foundation of all known life, would cease to function normally. Water would behave unlike any liquid you've ever seen. Metals would reconfigure into crystalline structures that don't exist on Earth. You wouldn't just die, your fundamental atomic identity would be erased, rewritten into some grotesque parody of matter that only a magnetar could sculpt. Even the most hardened spacecraft materials would surrender long before impact. Tungsten, prized for its high melting point, would vaporize at distances where the ambient temperature exceeds 10 million degrees. Carbon nanotubes, the strongest synthetic material ever made, would unravel like yarn in a shredder, and any attempt to shield against radiation would be laughable. Gamma rays here carry enough energy to penetrate lead as if it were tissue paper, while the magnetic field would twist protective force fields into useless knots. The only conceivable way to observe a magnetar up close would be through robotic probes built from entirely non-magnetic materials, perhaps ceramic or polymer composites operating for mere milliseconds before being annihilated. Even then, the data transmitted back would be fragmented, scrambled by the very forces the probe was sent to study. Magnetars don't just kill, they obliterate the very concept of visitation, enforcing their solitude with physics wielded like a cosmic guillotine. Every rule they break is a reminder. Some corners of the universe weren't meant to be explored, only admired from a very, very safe distance. Hollywood loves twisting cosmic horrors into blockbuster spectacle, and magnetars have taken their turn in the spotlight, though rarely with much regard for reality. Take the 2003 disaster Flick the Core, where Earth's magnetic field collapse is pinned on a rogue magnetic black hole, destabilizing the planet's core. The science here is pure fantasy. Real magnetars don't suck in matter like black holes, and their fields, while monstrous, fade with distance far too quickly to affect something as massive as a planet. But the film's premise taps into a visceral fear. What if a magnetar could reach out and crush our world? The truth is both less dramatic and far stranger. Then there's Doctor Who, which once featured a magnetar as a sentient, universe-ending entity, a creative liberty that overlooks their true nature. Real magnetars aren't conscious predators. They're chaotic objects, their violence born from physics, not malice. Even Interstellar, praised for its relativistic accuracy, took liberties by suggesting a neutron star's gravity could distort time enough to age an astronaut decades in hours. For magnetars, time dilation does occur, but you'd be vaporized by radiation long before you'd notice your watch ticking slower, the most persistent myth. That magnetars are magnetic black holes, a hybrid that simply doesn't exist. Black holes warp spacetime so severely that not even light escapes, while magnetars, however destructive, still obey the rules of visible physics. Their magnetism doesn't trap matter, it shreds it. Imagine the difference between a whirlpool and a blender. One pulls you in, the other turns you into pulp at a distance. Pop culture's magnetar tropes thrive on exaggeration, but reality offers its own eerie drama. Instead of planet-killing rays, real magnetars emit soft gamma repeater bursts, brief, universe-crossing flares that do occasionally rattle Earth's ionosphere. No sentient doom here, just nature's indifference. The next time a film warns of a magnetar apocalypse, remember, the truth doesn't need embellishment to be terrifying. These cosmic monsters are terrifying enough on their own terms. Studying magnetars demands technology as extreme as the objects themselves, telescopes that can peer into the most energetic corners of the electromagnetic spectrum, where X-rays and gamma rays reveal secrets invisible to ordinary optics. NASA Neutron Star Interior Composition Explorer, or NICER, mounted on the International Space Station, is one of humanity's sharpest eyes for this cosmic hunt. Unlike ground-based observatories hindered by Earth's atmosphere, which blocks most X-rays, NICER operates in the vacuum of space. Its array of 56 silicon detectors capturing photons with pinpoint precision. But it's not just about collecting light. NICER's real genius lies in its timing. Magnetars flicker and pulse with chaotic energy, and this instrument can clock those variations down to microseconds, unraveling the intricate dance of radiation as it escapes a magnetar's warped spacetime. Then there's the European Space Agency's Neutron, a powerhouse in X-ray astronomy with a sensitivity so refined it can detect the faintest thermal glow from a magnetar's surface, a whisper of heat amid the storm. Neutron's spectral resolution acts like a cosmic fingerprint scanner, dissecting the energy signatures of magnetar emissions to reveal their composition, magnetic field geometry, and even the quantum distortions of atoms trapped near the surface. When SGR 0501 plus 4516 erupted in 2008, Neutron caught the aftermath in stunning detail, showing how the star's crust cooled in real time, its X-ray glow dimming like embers in a dying fire. But these tools aren't infallible. Magnetars push detection tech to its absolute limits. Their gamma-ray flares, for instance, often saturate detectors, overwhelming instruments with energy spikes that blur into useless noise. Even the most advanced telescopes can't always distinguish between a magnetar's crust cracking and its magnetic field snapping, two events that might look identical in X-rays but stem from radically different physics. And then there's the challenge of distance. Despite their brilliance, magnetars are minuscule by cosmic standards, often appearing as single pixels of light. Without the ability to resolve surface details, scientists must reverse engineer their structure from flickers and flares, like diagnosing a patient through shadows on a wall. The next generation of observatories promises breakthroughs. The upcoming Athena mission, set to launch in the 2030s, will carry an X-ray spectrometer 20 times more sensitive than Neutron, capable of mapping magnetar magnetic fields in 3 dimensions. Meanwhile, projects like the Cherenkov Telescope Array aim to catch the highest energy gamma rays from magnetar flares, probing particle acceleration mechanisms that defy current models. But until then, every observation remains a puzzle, a fleeting glimpse into a realm where the laws of physics as we know them are not just bent but shattered. Each photon captured is a breadcrumb in a cosmic trail, leading us closer to understanding these magnificent, terrifying enigmas at the edge of reality. The future of magnetar research is brighter and more explosive than ever, thanks to a new generation of space telescopes and detectors designed to pry open the universe's most extreme magnetic vaults. Leading the charge is the European Space Agency's Athena X-ray Observatory, slated for launch in the 2030s. This isn't just another telescope, it's a quantum leap in X-ray vision, armed with a spectrometer so sensitive it could detect a single candle flickering on Pluto. Athena's mission, to map magnetar magnetic fields in 3 dimensions for the first time, peeling back layers of mystery like an interstellar archaeologist. Picture this: as a magnetar's crust fractures during a starquake, Athena will catch the resulting X-ray echoes with microsecond precision, tracing how shock waves ripple through the star's magnetosphere. These observations could finally reveal whether magnetars are the hidden engines behind cosmic rays, those ultra-high-energy particles bombarding Earth from deep space. But Athena won't be working alone. NASA Lynx X-ray Observatory, another powerhouse in development, aims to complement these efforts with even sharper imaging. Lynx's mirrors will resolve features on a magnetar's surface as small as a city block, unprecedented detail for objects only 12 miles wide. Together, these observatories could crack the code of how magnetars accelerate particles to near light speed. Current theories suggest their twisted magnetic fields act like cosmic slingshots, flinging protons and electrons across galaxies. Yet no one knows exactly how particles survive such brutal acceleration without disintegrating. Athena and Lynx might catch the process in action, watching as magnetars turn raw star stuff into interstellar bullets. On the ground, projects like the Cherenkov Telescope Array are joining the hunt from a different angle. While X-ray telescopes dissect magnetar emissions, this global network of gamma-ray detectors will scan for the aftermath ultra-high-energy photons produced when magnetar-accelerated particles collide with interstellar gas. It's like reconstructing a cosmic crime scene. The gamma rays are the smoking gun, revealing where and how magnetars fire their deadly beams, one tantalizing target. The mysterious anti-glitches where magnetars suddenly break. By syncing Athena's X-ray data with Cherenskov's gamma-ray readings, scientists might catch the exact moment a magnetar's magnetic rebellion steals its spin energy, a breakthrough that could rewrite textbooks on stellar mechanics. Meanwhile, China's Einstein probe, set to launch in 2024, will act as the universe's night watchman. Unlike Athena's deep dives, this wide-field X-ray telescope will constantly scan the skies for magnetar outbursts, alerting other observatories within seconds when a flare erupts. Time is critical. Some magnetar bursts last milliseconds, and catching them in real time could unveil what triggers these violent tantrums. The probe's lobster eye optics, inspired by nature's design, give it a panoramic view no traditional telescope can match, perfect for spotting cosmic flashbulbs in the dark. The most audacious plan, listening for magnetar quakes with gravitational waves. Future upgrades to LIGO and Virgo could detect ripples in spacetime from cracking magnetar crusts, offering a completely new window into their interior structure. Imagine feeling the vibrations of a star's surface from thousands of light-years away. Like holding a stethoscope to the chest of the cosmos. Combined with X-ray data, these whispers from Einstein's universe might finally answer whether magnetars harbor exotic states of matter, like quark-gluon plasma or free-floating strange quarks in their cores. Yet the biggest revelations may come from surprises. Every time we've built a better telescope, magnetars have defied expectations, unleashing flares where none were predicted, or going silent when eruptions seemed inevitable. As these new tools come online, one thing's certain: the universe's magnetic monsters still have secrets to spill. Whether they're the source of dark matter particles, the architects of fast radio bursts, or something even stranger, the next decade of magnetar hunting promises to be anything but predictable. Magnetars are more than just cosmic oddities. They're the universe's ultimate physics labs, offering conditions so extreme they shatter every experiment we could ever conduct on Earth. Take quantum electrodynamics, the theory describing how light and charged particles interact. In ordinary settings, its predictions are subtle, observable only in delicate lab setups. But near a magnetar, quantum effects dominate. Electrons don't just orbit nuclei, they're stretched into needle-thin spirals by magnetic fields trillions of times stronger than anything we can create. The vacuum of space itself becomes polarized, bending light in ways Einstein never imagined. It's as if the cosmos took quantum theory's fine print and blasted it across the sky in neon letters. Gravitational physicists are equally fixated on these stellar enigmas. Magnetars warp spacetime so severely that their surfaces experience time dilation measurable from thousands of light-years away. When their crusts crack in starquakes, the resulting vibrations could theoretically send ripples through spacetime itself. Future gravitational wave detectors might catch these tremors, offering clues about neutron star interiors that light alone can't reveal. Imagine decoding the density of nuclear posture or the friction of superfluid cores by listening to the echoes of a magnetar's quakes. It's like using a cosmic stethoscope to diagnose the heart of a star. Then there's particle acceleration. Magnetars whip protons and electrons to near light speed, creating gamma-ray flares brighter than entire galaxies. These aren't just cosmic fireworks, they're natural versions of the Large Hadron Collider, but with energies far beyond our reach. By studying how particles behave in such monstrous fields, scientists can test theories about cosmic rays and even dark matter. Some speculate that magnetar flares might produce hypothetical particles like actions, which could solve one of physics' biggest mysteries, the nature of dark matter. The real magic lies in magnetars' unpredictability. Unlike controlled lab experiments, these stars are messy, violent, and gloriously chaotic. A single outburst can rewrite textbooks overnight, as seen in 2020 when a Milky Way magnetar emitted a fast radio burst, a discovery that linked two of astronomy's biggest puzzles. That's the power of a natural lab. It doesn't just test theories, it blindsides us with questions we never thought to ask. From quantum quirks to space-time warps, magnetars are the universe's way of showing us where the edges of physics and our imagination truly lie. Given their terrifying power, it's natural to wonder, could a magnetar ever pose a threat to Earth? The short answer is yes, but the reality is far less dramatic than doomsday movies suggest. For a magnetar to truly endanger our planet, it would need to be uncomfortably close within about 10 light-years, a distance where its gamma-ray flares could strip away our ozone layer and trigger a mass extinction. Thankfully, the closest known magnetar, SGR 0525-66, sits safely 1,600 light-years away in the Large Magellanic Cloud. Even at that distance, its eruptions barely register as atmospheric static. Let's break down the math. A typical magnetar flare releases roughly 10 to the 40 ergs of energy, equivalent to 1 billion atomic bombs detonating at once. But radiation follows the inverse square law. Its intensity weakens with the square of the distance. By the time those gamma rays cross thousands of light-years, they've diluted into cosmic background noise. The infamous 2004 flare from SGR 1806-20, for instance, ionized Earth's upper atmosphere from 50,000 light-years away, but the effect was fleeting, no more disruptive than a minor solar storm. What about indirect threats like wandering magnetars drifting closer over millennia? Here, astronomy offers reassurance. Neutron stars, including magnetars, are born from supernova explosions so violent they often kick the remnants clear of their birthplaces. These kicks send them careening through space at hundreds of kilometers per second, but the distances are so vast that the odds of one barreling into our cosmic neighborhood are astronomically low. Even if one were headed our way, we'd have millennia of warning to track its trajectory. The real risk isn't a magnetar's proximity, it's our own detection limits. Current surveys have catalogued barely 30 magnetars in the Milky Way, but models suggest there could be dozens more lurking undetected. Some might be dormant, their magnetic fields too weak to flare visibly. Others could be obscured by interstellar dust, but even if we've missed a few, the sheer volume of space ensures they're far enough to be harmless. The galaxy spans 100,000 light-years. Even a few dozen magnetars scattered across that expanse are like fireflies in a football stadium, visible but never close enough to burn. So while magnetars are undeniably monstrous, their danger is confined to sci-fi fantasies. The universe, it seems, has built-in safeguards placing these magnetic leviathans so far away that their fury becomes just another light show in the cosmic theater. For now, we can study them, marvel at them, and rest easy knowing they're the universe's problem, not ours. Despite everything we've uncovered about these cosmic enforcers, magnetars still guard some of their most perplexing secrets, puzzles that keep astrophysicists awake at night. One of the biggest mysteries, why some of these magnetic monsters suddenly go quiet. Take XTJ1810-197, a magnetar that roared to life in 2003 with violent X-ray bursts, then faded to near silence by 2008. The star didn't vanish, its rotation and magnetic field appeared unchanged. So what flipped the switch? Current theories suggest some magnetars might develop thicker crusts over time, acting like cosmic insulation that traps magnetic energy beneath the surface. Others speculate that internal superconductors, exotic quantum fluids in their cores, could gradually short-circuit the magnetic dynamo. But without direct observations of this shutdown process, we're left guessing whether it's a slow fade or a sudden collapse of internal magnetic structures. Then there's the enigma of magnetic field decay. We know magnetars don't stay ultra-powerful forever, their fields weaken over millennia, but the exact mechanism remains hotly debated. Some models suggest the fields dissipate through gradual ohmic decay, where resistance in the star's interior converts magnetic energy into heat. Others propose something far more dramatic, Hall drift, where the entire magnetic structure gets reconfigured as free electrons drag field lines through the neutron soup of the crust. The smoking gun might lie in middle-aged magnetars like SGR 0418+5729, whose X-ray emissions show strange periodic dimming, possibly the death throes of a once mighty field slowly unraveling. But with decay timescales spanning tens of thousands of years, catching one in the act is like trying to watch a mountain erode in real time. But nothing baffles scientists quite like the trigger for giant flares, those split-second eruptions that outshine galaxies. We know they're linked to starquakes and magnetic reconnection, but why do some fractures release city-leveling energy while others unleash planet-shattering blasts? The 2004 flare from SGR 1806-20 offers clues. Minutes before the main explosion, satellites detected subtle X-ray oscillations, like a teacup trembling before a quake. This suggests flares might begin deep inside the crust, where pent-up magnetic stress reaches a breaking point. Yet we've also seen failed flares where similar precursors fizzle out without catastrophe. The difference could come down to the star's magnetic topology, how tangled its field lines are beneath the surface. Imagine twisting a rubber band tighter and tighter until it snaps. Some configurations release energy smoothly, while others detonate catastrophically. Perhaps the most tantalizing question is whether these phenomena are connected. Could a magnetar's sudden quieting accelerate its field decay? Might the crustal changes that mute flares also destabilize the magnetic architecture? Every new observation adds pieces to the puzzle, but the full picture remains frustratingly out of focus. What's clear is that magnetars still hold the keys to understanding some of the most extreme physics in the universe, if we can just decipher their cryptic behavior. Until then, these magnetic phantoms will continue to challenge our assumptions, surprise us with their outbursts, and remind us how much we still don't know about the violent machinery of the cosmos. Could magnetars, those cosmic powerhouses of pure magnetic fury, hold clues to one of the universe's greatest mysteries, dark matter? It sounds like the plot of a sci-fi thriller, but some physicists are seriously considering whether these ultramagnetic neutron stars might be nature's dark matter detectors. Here's the wild premise: dark matter, which makes up 27% of the universe's mass, barely interacts with normal matter. Yet when it does, the collisions should produce faint bursts of energy signatures too subtle for most telescopes to catch. But magnetars aren't most telescopes. Their monstrous magnetic fields could amplify these whispers into detectable screams. Take the hypothetical action, a leading dark matter candidate. These ghostly particles, if they exist, should convert into photons in the presence of strong magnetic fields, exactly the environment around a magnetar. Picture an action drifting too close to a magnetar's magnetosphere. The instant it brushes against those trillion Tesla field lines, it could morph into an X-ray photon, flashing like a cosmic Morse code against the star's turbulent glow. In theory, observatories like Chandra or XMM Newton might spot these anomalous X-rays, especially if they cluster at specific energy levels unrelated to known magnetar activity. Even stranger are proposals that magnetars themselves could produce dark matter. Quantum physics allows for virtual particles to pop in and out of existence in extreme environments. Near a magnetar's surface, where magnetic fields distort the quantum vacuum itself, these fleeting particles might include WIMP, weakly interacting massive particles, another dark matter contender. If conditions are just right, the magnetar's energy could kick these virtual WIMP into reality, ejecting them into space as tangible dark matter. It's like a cosmic 3D printer, except instead of plastic, it's spitting out the invisible scaffolding of the universe. The most tantalizing hints come from anomalies we've already observed. Some magnetars emit unexpected X-ray lines, tiny spikes at specific energies that don't match any known atomic transition. Could these be the fingerprints of actions converting into light, or perhaps traces of dark matter particles decaying in the magnetar's grip? The challenge is untangling these signals from the star's own chaotic emissions. It's like listening for a single wrong note in a symphony played at jet engine volume. Skeptics argue that magnetars are too messy for clean dark matter detection. Their flares, starquakes, and magnetic reconnections create a cacophony of high-energy noise that could drown out any dark matter signal. But proponents counter that this very chaos might hide patterns, like how lightning storms can reveal atmospheric chemistry. If certain X-ray bursts occur during magnetar quiet periods, or cluster in directions where dark matter is thought to accumulate, it could point to an exotic origin. Future telescopes might settle the debate. The European Space Agency's Athena mission, launching in the 2030s, will study magnetar X-rays with unprecedented precision, possibly catching action conversions in real time. Meanwhile, gravitational wave detectors could hunt for tremors caused by dark matter particles colliding with a magnetar's core, events that would ripple space-time subtly but distinguishably from ordinary starquakes. Whether magnetars are dark matter factories, detectors, or just cosmic red herrings, their role in this mystery underscores a profound truth. The universe's most extreme phenomena might be the keys to unlocking its deepest secrets. Every flicker of anomalous light from these magnetic monsters forces us to ask, are we seeing physics as we know it, or the first hints of something entirely new? Every cosmic powerhouse must eventually burn out. Even magnetars, with their unimaginable magnetic might, are no exception. But what happens when these titanic magnets finally lose their grip? The answer depends on a delicate tug-of-war between gravity, magnetism, and the bizarre physics lurking inside their cores. One fate might seem inevitable: collapse into a black hole. After all, magnetars are already on the knife's edge, packing multiple suns' worth of mass into a sphere no wider than Manhattan. Their crushing density constantly battles gravity's pull, and if their magnetic fields decay too slowly, they might tip the scales. Here's how: as a magnetar's spin slows and its magnetic energy bleeds away through radiation, the outward pressure keeping its structure intact weakens. If the core, already a soup of hyper-compressed neutrons, crosses a critical threshold, it could implode without warning. No dramatic explosion, just a sudden, silent vanishing act as space-time folds inward. But there's another, quieter possibility. Magnetars might instead fade into obscurity as inert neutron stars, still unimaginably dense but stripped of their magnetic fury. Over tens of thousands of years, their colossal fields dissipate, drained by relentless particle acceleration and crustal cracking. The once violent surface cools, its X-ray glow dimming to a faint infrared whisper. Left behind is something resembling an ordinary pulsar, albeit one with a haunted past: the wild card internal composition. Some theories suggest magnetars harbor cores of exotic matter, free quarks, or strange matter that could abruptly destabilize. A sudden phase transition inside the star, where neutrons dissolve into their constituent particles, might trigger a catastrophic chain reaction. One moment a magnetar, the next a quark star or a black hole. Oddly, their magnetic fields might also offer an escape from total collapse. Unlike ordinary neutron stars, a magnetar's field is woven so tightly into its structure that its decay could release energy gradually, like a cosmic pressure valve. Instead of imploding, it might stabilize as a dead magnetar, a dense, weakly magnetic remnant drifting through the galaxy's graveyard of stellar corpses. The universe has likely already shown us both outcomes. Some black holes might be the graves of ancient magnetars, while certain dim, slow-spinning neutron stars could be their exhausted descendants. Until we catch one mid-transformation, Their final fate remains a cosmic coin toss, one where gravity and magnetism duel for supremacy at the edge of oblivion. From their birth in cataclysmic supernova to their eventual fade into cosmic obscurity, magnetars stand as some of the most extreme laboratories the universe has ever crafted. These celestial powerhouses redefine the limits of physics, where magnetic fields trillions of times stronger than Earth's twist atoms into bizarre shapes, where the vacuum of space itself polarizes under unimaginable strain, and where starquakes unleash energy rivaling entire galaxies in the blink of an eye. Every flicker of X-rays, every gamma-ray burst, and every anti-glitch forces scientists to rewrite the rulebook, proving that reality can be far stranger than fiction. But magnetars are more than just cosmic curiosities. They're keys to unlocking some of the universe's greatest mysteries. Their flares might reveal the origins of fast radio bursts. Their magnetic decay could shed light on quantum vacuum effects, and their very existence pushes our understanding of matter under conditions no lab could ever replicate. Their natural particle accelerators, gravitational wave generators, and perhaps even dark matter detectors, all wrapped into one terrifyingly beautiful package. As we peer deeper into the cosmos, magnetars remind us that the universe thrives on extremes and that every discovery raises new questions. What other magnetic monsters lurk in the darkness? Could some unseen magnetar hold the secret to unifying physics' greatest theories? The hunt is far from over. If these cosmic enigmas captivated your curiosity, smash that like button. It fuels our journey to uncover more mind-bending wonders of the universe. From black holes to neutron stars, the cosmos is packed with phenomena that defy imagination, and your support helps bring those stories to light. Let us know in the comments which cosmic mystery we should explore next, because when it comes to the universe's wildest creations, the adventure has only just begun.